Okay, so welcome back. This is the second and last lecture of Chapter 5 for Advanced Placement Chemistry. Last time I left you off about here with the ideal gas equation, PV equals nRT. It's the equation we're going to use quite a lot this chapter. So we're going to talk about STP, standard temperature and pressure, 0 degrees Celsius. So for us that'd be 273.15 Kelvin. 1 atmosphere is pretty normal, so we'll use that as well. And so we know that at STP, 1 mole of an ideal gas occupies 22.4 liters. That is useful to know. And so PV equals nRT can be rearranged to solve for any of these variables that you need to, and we'll use it all the time. So it gives us R is what they've derived given this 22 liters thing, and R is one that you'll want to memorize. It's 0.0821 liters atmosphere per mole Kelvin, and you'll use it so much that you'll memorize it. So feel free to write that down as well as this equation PV equals nRT. You will use it a lot for book questions. So here they would ask, what's the volume in liters occupied by grams of hydrochloric acid at STP? So that tells us our temperature is 273.15, our pressure is 1 atmosphere. N is the number of moles, so we'll have to get grams to moles by just adding up, hydrogen's 1.01, chlorine's 35.45, I think, and you could add those and get your grams per mole, and then solve for V. And so here they write their equation, PV equals nRT. They rearrange for volume right away in the beginning. Your call, that works just fine. Temperature standard, like I told you, and there's pressure, and then here is them solving their grams per moles hydrochloric acid to get moles. That's N, 1.37. So from there, it's a pretty simple equation. If you keep track of your units, you'll know you're doing it right if your units are correct. So atmospheres cancels atmospheres, and moles crosses off with moles, Kelvin and Kelvin. We're supposed to be finding a volume, and the only unit we're left with is liters, so we know that we're probably in good shape there. And sure enough, we are. So volume at 30.7 liters, and that would be just fine. So here's another one, argon, inert gas, light bulb at this pressure, 1.2 atmospheres, 18 degrees Celsius, is heated to 85 degrees Celsius at a constant volume. What's the final pressure in the light bulb? So here, there's a couple different equations you could use if you looked at that equation bank. But if it says it's at constant volume, we can probably not worry too much about the V. So it's just your moles to R over V equals P over T. Those are going to be constant. And so pressure 1 over temperature 1 equals pressure 2 over temperature 2. It's kind of like PV over T equals PV over T, the combined gas law. Just we know that volume is constant. So then we can solve for P2 with the values they give us in the question. And hopefully that would be pretty easy. Starting with PV, nRT, and getting to that was a little weird for me. I'd probably just use PV over T equals PV over T, because I remember that as the combined gas law. So 1.48 atmospheres, that's how you do something like that. Density calculations aren't something that I saw a lot of while I was doing the questions in the back of the book, but here's how you'd solve it. Density is mass over volume. That's really for any science class, and here the mass is P times M, where M is mass in grams, and this capital M is the molar mass of the gas, so our grams per mole from the periodic table. And here you could solve just for molar mass with density RT over P. Again, not something I saw a whole lot of when I was doing these problems, so I don't know if I'd lose any sleep over that. But if you had to do it, and they give you volume, and they give you grams, they gave you pressure, they gave you temperature, could you solve for molar mass? Sure. Density RT over P, so we've got to find density in our grams per liters, 4.65 grams, 2.10 liters, that's mass over volume, so it'd be grams per liter, so that takes care of the density part. R we already know, temperature they give to us, pressure they give to us, so from here on out we're really just filling in values that are right there in the problem. This is the one I told you you'd want to memorize, 0.0821 liter atmosphere per mole Kelvin. Here's their temperature. They just took this 27, and they added 273.15, and then the pressure from the problem at 1 atmosphere. So not too terrible, a little lengthy, but not too terrible. And so they would be left with grams per mole, which is molecular mass value. So stoichiometry is really, I hope, something you remember from Gen Chem. It's really not that bad. Basically what you do is you use the balanced chemical equation as molar equivalents, and then you can get from anything really to moles of anything else once you have a balanced equation. And so here, they want volume of carbon dioxide, which is on our product side. They give us a temperature, they give us a pressure, they give us a mass of glucose used up in the reaction. And so if we can get that mass to moles, and then get moles of what we have, glucose, to moles of what we're interested in, carbon dioxide, then we can find the volume with PV equals nRT. And so here's how you would do something like that. You take your 5.6 grams of glucose they give you in your equation, but we don't want grams, we want moles, because these are molar ratios up here. That's what our coefficients are. And so you'd calculate, what's 12.01 times 6 plus 12 times 1.01 plus 6 times 16, and you'd get this 180 number, and that gives us moles of glucose, which is good, but we don't want moles of glucose, we want moles of carbon dioxide. So we use this ratio of 1 mole of glucose to 6 moles of carbon dioxide, gets us to CO2. And then once we're at moles of carbon dioxide, we can use our PV equals nRT to find our volume. So there's 0.187 moles CO2, that'll be our N in that equation. So volume equals, we've rearranged PV equals nRT to just solve for V. That becomes N, R is 0.0821, temperature is 37 plus 273.15, and pressure is 1 atmosphere. Looks something like that. And that's a done deal. So hopefully that is a problem you will see again. Not that same problem, but problems like that. I've come across a lot of those as I was working through your book questions. So be prepared to utilize that information in the not too distant future. Dalton's law of partial pressures, again, one that we're going to have to calculate. For this, we say volume and temperature held constant, and it's not terribly complicated. Basically, if we had gas that had pressure 1 from just this gas that is the gray molecules here, and pressure 2 from the red molecules, if we combine those gases, then the total pressure of the system would equal the partial pressures of individual gases that make up the system. So not conceptually terrible, I hope, but here's how you would use it. Two gases, A and B, are stuck in this container. You can find the number of moles of A and the number of moles of B, and then for your total pressure, you have to use what's called a mole fraction. And that's the part of these problems that can get a little bit tricky, but it makes a lot of sense actually. The mole fraction of A, these little red particles, is the number of moles of A, the little red particles, divided by the number of moles of all the gases. And so a mole fraction kind of makes a lot of sense. It's the number of moles of what we're interested in divided by the total. So it's really not too terrible. Once you do a couple of them, they come pretty easy. And here's the mole fraction for the green gases, same way, what we're interested in over the total. And so the mole fractions, you'll see the equation in your book is X subscript I, and we'll be using that quite a bit. And so here's the formula you'll see, PA equals XA or PT, or in your book it's P little I equals X little I PT, and all that is the partial pressure of gas A is equal to the mole fraction of gas A multiplied by the total pressure. So not too bad there. And here you can do the same thing with B. You just have to change that mole fraction to, of course, the mole fraction for molecule B. And once you do a couple of those problems, they're really not too bad. So feel free to write this down. It is in your text as well. You can find that. And there's the mole fraction, number of moles of what you're interested in, divided by the number of moles total. And so here's what it would look like in a problem. We had a sample of natural gas, and it's got 8 moles of methane, 0.4 moles of, what would that be, ethane, and 0.116 moles of propane. So if the total pressure of the gas is 1.37 atmospheres, what's the partial pressure of propane? And so you say, okay, propane, I've got 0.116 moles of propane, and I've got these moles here that are going to add to my total. So I can find my mole fraction xi without too much trouble. I just say propane is 0.116 moles divided by 8.24 plus 0.42 plus 0.116. So I'm adding all of these up, and that's going to give me x for propane, 0.0132. Now you note that it doesn't have a unit, because if we're dividing moles by moles, we're getting a ratio here, not anything with a unit at the end. So that's something to be aware of. So then all we have to do is multiply our mole fraction by our total pressure, PT, which is 1.37 atmospheres, given to you in the problem, and you have the partial pressure of propane is 0.01 atmospheres. So that's how you'd solve a problem like that. Here's how they calculate that, where you create a gas, and the gas is then released through a liquid, and then that'll be the pressure of that gas, along with the vapor pressure of water, is kind of how a lot of gases can be collected. So here's a graph of vapor of water and temperature as the temperature goes up, as does the pressure for water. Not anything you need to memorize. The practical application of this is scuba diving, which you heard in Gen Chem. As you descend further down a water column, the pressure increases. As the pressure increases, we're able to diffuse more gases into the capillaries of the lungs, and so that's why we have to also ascend through a water column very slowly. Otherwise, divers can get the bends, which I guess is not fun. Kinetic molecular theory of gases, not too complicated. A gas is composed of molecules, no kidding. They're separated by great distances. The molecules can be considered to be points. They possess mass but have a negligible volume. They're in constant motion, random directions. They collide with each other, and collisions among molecules are perfectly elastic, which means if two hit, they will bounce off of each other without, hopefully, any real bonding or attraction to one another. Gas molecules do not exert attractive or repulsive forces on one another. That's what we use for calculations. In the real world, that's not necessarily 100% true, but it makes calculating easy. The average kinetic energy of molecules is proportional to the temperature of the gas in kelvins. Hotter the gas molecule, the more kinetic energy it moves. Hotter the gas molecule, the faster it moves. Any two gases at the same temperature have same kinetic energy. So that's the kinetic molecular theory of gases, which just means the theory that little molecules have kinetic energy and are moving and bouncing into each other. You can calculate kinetic energy 1/2 mv squared. They have u, whatever you want to use for velocity, speed, that's what it is. So kinetic theory of gases, compressibility of gases, Boyle's law. For Boyle's law, pressure is proportional to collision rates, and collision rate is proportional to the density of the number of molecules you have. So that's how we get pressure is proportional to 1 over v. Charles' law is, of course, temperature now, so pressure is proportional to collision rates. Collision rates are proportional to average kinetic energy. Average kinetic energy is proportional to temperature, so then pressure is proportional to temperature. So this is just kind of showing us how kinetic theory helps us explain all of the gas laws we've learned. Avogadro's number. Collision rates are proportional to density. The number of density is proportional to the moles of the gas, so pressure is proportional to the moles of a gas. Dalton's law of partial pressures says molecules don't attract or repel one another, so pressure exerted by one type of molecule should be unaffected by the presence of another gas, so then we can simply add the individual gases to get the total pressure of all of the gases. This is an apparatus for studying molecular speed, where they have this rotating slit and a detector on the end, the motor to turn the whole apparatus, and then as molecules are kind of shot through on this detector, the average molecules form this big arc, with the slow molecules being on one end, the fast molecules being on one end, and the average is in the middle. This is the idea that molecules have different speeds. Here's molecular speed and the number of molecules. 3 different temperatures, so if you change temperature, you change the speed. And then different gases at the same temperature, if you look at speed and the number of molecules. Chlorine gas at 70 grams per mole is rather slow. Nitrogen gas at 28 is quite a bit faster. And then helium gas, very, very light, 4 grams per mole, is kind of the fastest, you could say. So that's a little look at molecular speed and mass, how those two things depend on each other. Gives us this equation that the root mean square speed of a gas is equal to the square root of 3RT divided by the molecular mass. If you want, you can look at page 206 and 207 in your text. It's important to know that this R, this constant, is not the 0.0821 that we've been used to and we've been using. It's actually 8.314 joules per Kelvin moles. The other weird thing to note about this equation when you use it is the molecular mass is in kilograms per mole, not grams per mole. So that's a weird equation, a really weird equation, but we will use it in class. It's not too bad, but knowing those two differences are incredibly important, and all it does is it tells us how fast a molecule is. That's the long and short of that. This is a image of a graph of Bose-Einstein condensate, super cold atoms. Atoms behave really odd when they become very, very cold, and they start to deviate a little bit from normal behavior. So we got to talk about diffusion and effusion now. Diffusion is gradual mixing of molecules, just because of their kinetic properties. Just because they're moving all around, they're going to mix a little bit. And here we see we've got NH3, which is diffusing. We've got HCl, which is diffusing. And because NH3 is so light and relatively quick, they're going to start to mix kind of over here. NH3 will sort of be a little quicker than HCl. So NH4Cl is what's forming over here. So we can kind of see that stuff. Their rates are proportional to the square roots of their molecular masses. And so effusion, as opposed to diffusion, is effusion has to occur through a small hole. So they have to escape from one compartment to another. And here that is, again, just like before, it's related to their molecular masses, the square root. And that's not one we're going to see a lot of problems over. But here's one that's a little tricky. Nickel forms a gas compound with the formula NiCOX. What's the value of X given that under the same conditions, methane effuses 3.3 times faster than the compound? And so what we can say is, okay, R1 is equal to 3.3 times R2 because we're 3.3 times faster than R2. And the molecular mass of CH4 is 16 grams per mole. So then we can kind of rearrange this equation here of R1, R2, M2, M1 to solve for M2, the molecular mass. And we have R1 over R2 squared times M1. And so we get 3.3 squared times 16 equals 174.2. And then we look at what it would take to add up to 174.2 given the molecular mass of what we already know, and it's about 4. So kind of a tough problem, not one that we're going to deal with a whole lot. For deviations from ideal behavior or ideal gas law, PV equals nRT. Not all gases follow that. We wish they did. It's nice when they do, but really they don't. Here's the ideal line right here for your ideal gases, PV equals nRT. But there are some gases that are attracted to each other. There are some gases that are repelled away from one another, and so you get these areas where if they're attractive or repulsive forces at work, they're going to deviate from ideal gas behavior. Here's the effect of intermolecular forces affecting pressure. Is it a random collision? Not really, because these are being attracted to one another, so it's going to affect our equation. So you can do some work with non-ideal gases, but our equations get a little more tricky than PV equals nRT. Now we have PV equals nRT, but pressure and volume have to be adjusted to non-ideal situations. So they're corrected, pressure and volumes, and they give you formulas over here. You have to refer to these tables in order to do those problems. Not something we're going to work a lot with. So with that,